Before we dive in, let me just say briefly what the moment of a force or torque is, in case you're not familiar with the term. It's the ability of a force to make something rotate. Now don't confuse the word moment with a short time, as in I'll be with you in a moment. That's not the meaning. Don't confuse the word moment with momentum, which is a different thing. The moment of a force is its ability to make something rotate. And we use different expressions when referring to it. We could say the moment of a force about a point, or the moment of a force, or just the moment, or sometimes we use the term torque, and torque is another word meaning moment of a force. I'm going to stick to using the word moment most of the time. When we do calculations, we can work out the moment. It's got a size. And the symbol we use, well, people use capital M's or sometimes a Greek letter tau, a small tau, which is that symbol. I don't like M because it looks too much like mass, so I will use tau to remind us of torque, tau. Let's talk about some terms you need to know. What are they? Fulcrum, point of application, and very important, line of action. Fulcrum first. What is a fulcrum? Well, it's basically just a posh word for a pivot. Suppose you have a seesaw, simple one, plank balanced on an edge like that, pointed edge. The point of contact is the fulcrum. It acts as a pivot. The top part, the yellow plank, can rotate around that pivot. And a fulcrum just means a pivot. It doesn't have to be something resting on an edge. It could be this sort of arrangement where you have a hinge. And a door hinge is a fulcrum. The joint in a pair of scissors is a fulcrum. So it's just a pivot in simple terms. What about these terms? Point of application of a force and the line of action of a force. Well, there's a block resting on the ground. Let's apply a force to it. 20 newtons to the left. The point of application is pretty obvious. It's a point on the object where the force is applied. So it's shown here by the tip of that arrow. What about the line of action of the force? Well, the line of action is a line which passes through the point of application and goes in the same direction as the force. So in fact the force lies on this line. Let me draw it. It's that blue line. That's the line of action of the force. In principle it can be extended indefinitely to the left or the right, or whatever direction is relevant. And that's a very useful concept, the line of action of the force, the line that the force is on. Let's just look at another force, 20 newtons to the left. In vector terms it's the same. It's got the same magnitude, it's got the same direction, but it's got a different line of action. The point of application is now up here, and the line of action of this force would be that. Which of those two forces do you think is most likely to cause this object to topple over, assuming there's friction at the bottom so it can't slide? Is one more likely than the other? I'm sure you know from your experience that the 20 Newton force at the top is more likely to make this topple over. And the turning effect of this force, 20 newtons, depends on how far the line of action is from the floor. Of course, a line of action doesn't have to be a horizontal or vertical line. If you have a force like that, where do you think its line of action is? You realise that would be the line of action. Right, now we can get on and talk about what we mean by the moment of a force, or torque. And I'm going to work out a couple of examples before I give you a definition. So let's take this very simple situation of a seesaw. What's going to happen if we put a weight on the right hand side? Well, you don't have to know excuse me, you don't have to know very much physics to know that the bottom of the right hand side will go down. So the whole seesaw has rotated clockwise. because of this force on the right hand side. So we could say that the weight has a clockwise turning effect, or to use the language we want to, we can say the weight has a clockwise moment about the pivot. It's got a tendency to make this thing rotate clockwise about the pivot. What would I have to do to return the seesaw to the level? Well, one thing I could do is apply a force on the left. The weight was 10 newtons on the right. If I apply a force of 10 newtons on the left, the same distance from the pivot that the weight was, the 10 Newton force will have the effect of making the seesaw rotate anti-clockwise or counterclockwise, purple arrow. So we can say that the force we've shown in purple has an anti-clockwise or counterclockwise turning effect, or in the language of moment we'd say it has an anti-clockwise moment about the pivot. It's got a tendency to cause rotation in an anti-clockwise direction, with the pivot being the centre of rotation. So get back to our horizontal balanced equilibrium state. Of course, I could achieve that by pressing it at a different point on the left of the seesaw. I could press a bit nearer to the fulcrum. If I did that, would I need a bigger or smaller force, do you think? And I hope you know from your experience that if you press nearer to the fulcrum, nearer to the pivot, you would need a bigger force than 10 newtons to balance it. So if applied nearer to the pivot, the balancing force needs to be bigger to provide the same turning effect, the same moment. Now, here's an example for you to think about. Let's look at an hexagonal nut. So I hope you know when you have a nut, usually you turn it clockwise to tighten it or anti-clockwise to loosen it. And we use a spanner, or some people call it a wrench, to do that. There's a rather crude spanner. Now, I'm going to ask you some questions. Let me mark a number of different forces you could apply to the spanner. Quite a lot. You can have a look at those in a minute, but what I want you to do is try answering these three questions. Which force or forces has or have a zero moment? That means no turning effect. So some of these forces may or may not make the nut turn. Can you identify which have a zero moment, no turning effect? Which force do you think has the biggest clockwise moment, the biggest clockwise turning effect? And which force do you think has the biggest anti-clockwise moment? Pause to think about those. Well, I hope you've done it. If you look carefully, forces A, forces D, and forces E point directly at the centre of the nut. And if you apply a D or E, they are not going to cause any rotation. They're directed at the centre, not to one side of the centre. So the answer to the first question was A, D and E. Which force has the biggest clockwise moment? Well, I hope you can see that only B and C have clockwise moments. And I hope you know that if you apply a force further away from the fulcrum, it has a bigger turning effect. It's a lever. So the answer to the second question is C. C is furthest away from the fulcrum and it will have a bigger turning effect than B. And the last one, similar argument, is G, that's got the biggest anti-clockwise or counterclockwise moment.